Today's discussion topic is fiber configuration and NEPs in card sliver. Let us look at the shapes of fibers in card sliver. Now, certain shapes are depicted in this slide. What we see here that the configuration or the shape of the fibers are many. We can see that some fibers are straight in nature, like the fiber shown here. Some fiber ends are bent in the form of a hook, we call them hook fiber. Some fibers are bent and the two limbs of the hook are almost similar in length, we call them U shaped hook fiber. Some fibers are forming a loop, so we call it loop fiber. Some fibers are entangled in nature, like this fiber. So, this is entangled fiber, and there are fibers which are more or less straight, like this fiber also, as told earlier. So, there are innumerable shapes which are available in the card sliver. Now, if we want to visualize these shapes, then what technique is available with us, so that we can see the shape of the fibers. If I take a fiber sliver and then see it under microscope, then we will find that there are many fibers, but it will be very difficult to know exact shape of those fibers, because all the fibers are of same color. So, there is a technique known as tracer fiber technique, which can be employed to study the shape of fibers in a sliver. So, what is this technique that we are going to discuss? In this technique, first of all, a small quantity of fiber is dyed with any commercial whitening agent like Tinopol BVN. After dyeing this, we dry the fibers in room temperature, and once it is completely dried, we have to open it by hand using our fingers. Once the fibers are separated from each other, now these tracer fibers are mixed with normal fibers. It is not dyed fiber, these are tracer fibers on a finisher scotcher lattice, and then we have to form a lap, so that all these tracer fibers get mixed up with the rest of the fibers, and then a lap is produced. So, this one is tracer fibers, not dyed fibers. The next step, now we process the lap on a card and collect the wave samples from the card, or we can also collect the sliver and then place this wave or the sliver on a black board. So, we can collect number of samples and put them on black boards. Next, the direction of the delivered wave or the sliver is to be marked on the blackboard, so that we can find out later on in which directions the fibers were delivered. So, which is the forward directions and which is the backward directions. Now, these collected samples have to be seen under UV light source in a dark room. The configuration of the tracer fibers would be distinctly visible, as they will all glow under UV light. So, once they are visible, it becomes easy for us to note down the configuration. We can trace the configuration on piece of paper, or we can take photograph, and later on we can see the photographs and study the configuration. So, this is the technique known as tracer fiber technique. This technique has been used by many people to study the configuration of fibers. Now, here is a table where the fibers have been classified according to their configurations. And if we look at this table, what we see here that there are fibers having hook in the leading directions, we call them leading hook fibers. There are fibers with a hook in the trailing part of the fiber, we call them trailing hook fiber. There are fibers or both the ends are hooked, we call it both end hook fiber. Then there are fibers, some of them are straight, we call them straight fibers, and there are fibers which do not fall into these categories, and therefore, we put them into another separate category called others. So, there are 1, 2, 3, 4, 5 different categories, and what we see here is this, that generally trailing hook fibers are more in numbers than leading hooks. This is one important observation which has been shown by many people. Around 50 to 60% of the fibers are trailing hook fibers and 20 to 30% are leading hook fibers. This is also the typical distribution of the hook fiber in a sliver. Straight fibers are not really many, but there are definitely some straight fibers as well, and we can also see that the Doffler speed can affect the pattern of hook formations. That is, in this case, for two different Doffler speeds 10 rpm and 18 rpm, we can see the configurations, and obviously the configurations are different in terms of numbers of the hooked fibers in different categories. So, we can also say that Doffler speed plays a role in deciding the number of hooks in different categories. From here, we go to the next slide, that is mechanism of trailing hook formations, that why these hooks get formed, why trailing hooks are more in number than leading hooks. So, in the diagram we see there is a cylinder and there is a Doffler, and let us concentrate on a fiber AB as shown in the diagram. Now, as the fiber is carried forward by the cylinder and the fiber approaches the Doffler surface, the leading end of the fiber AB comes into contact with the Doffler, and then it keeps on traveling at the speed of Doffler. Like the fiber original position is A0 B0, position 2, let us say this is position 1, where the leading end has landed on the Doffler surface, but the trailing end is still in contact with the cylinder. Now, in this situation, what will happen? The leading end is in contact with the Doffler, so this end will move at the speed of Doffler. The trailing end is in contact with the cylinder, so this will move at the speed of cylinder. Therefore, the two ends of the same fiber will move at two different velocities. We all know that the velocity of the cylinder is much more than the velocity of the Doffler. So, if V c is the velocity of cylinder and V d is the velocity of the Doffler, then we all know that V c is much greater than V d. So, what will happen? during the process of transfer, the end B will quickly pass through the transfer zone. So, the end A which is in contact with the buffer still remains on the buffer, but the other end B now moves forward and takes the position A 2 B 2. Now, what happens is this situation, that as a result of this the fiber turns, that is B comes in front of A. So, earlier the end A was in front of B. Now, while going through the transfer zone, the entire fiber reverses and B moves forward than A, because end B is in contact with the cylinder. After this fiber get transferred and this will appear like this. Let us say this will be A 3 B 3, and we see that the fiber will appear from the buffer as a trailing hook fiber. End B gets combed by the cylinder wire points or cylinder teeth, hence the end B may not have a hooked end, whereas end A which lasts on the buffer surface remains caught there in the form of a hook, and therefore, finally, when this fiber emerges from the buffer, it is in the configuration of a trailing hook. This is the mechanism of trailing hook formation. From there, we can say that fibers situated on the surface of cylinder fiber layer are positively controlled by buffer, and their front ends form mostly trailing hooks. From here we go to the next slide in order to understand the mechanism of leading hook formations. The diagram is shown here, and let us consider another fiber A B. The different positions of the fibers are also shown in the diagram. Now, what we see here, that the fibers situated in the lower fiber layer on the cylinders are peeled off by the buffer only through its contact with the top layer. On the cylinder we have a thick layer of fiber. So, some fibers are directly in contact with the buffer wire on the cylinder wire points. Similarly, there are fibers which are lying on the cylinder, but may not be positively gripped by the wire points of the cylinder. They are in contact with other fibers which are in turn in contact with the cylinder wire points. So, these fibers are basically on the top layer of the cylinder. So, in the process of peeling off, what happens? The trailing end of the fibers which are embedded in the cylinder wires, after losing contact with the cylinder, gets whipped up due to sudden relaxation and form a leading hook. Let us look at the fiber here now. Fiber AB approaches the buffer. So, what happens? The end comes here into contact with the buffer like here, and then as the cylinder wire points are combing the end point of the same fiber, these fibers loses contact, they are peeled off from the surface of the cylinder, and the end suddenly whipped up due to relaxation of stress, as shown in the diagram as A 2 B 2. With the formation of thicker fiber layer, the proportion of indirectly controlled fiber increases, and therefore, this proportion of leading hook. So, when this fiber gets whipped up, then we see that fiber comes as leading hook from the surface of the Doffer. This is how the leading hooks are getting formed. Then from there we go to the mechanism of another theory for the formation of leading hooks, and it shows that the front end of a fiber moving with the velocity of the cylinder comes into contact with the relatively slower moving Doffer surface, and when the end hits the Doffer surface, the front part of the fiber moves at a slower speed, whereas the back part is moving at a higher speed, because the back part of the fiber is in contact with the cylinder and the front part is in contact with the Doffer. And as a result of this, the fibers get buckled in the form of a hook, and in the same way they get transferred to the Doffer. If the fiber is loosely held by the cylinder, which depends largely on the nature and extent of positive control exercised by the cylinder on the rest of the fiber, it gets transferred without reversal and hence form a leading hook. So, what we see here, the fiber initial position is 1, the next position is coming over here A 1 B 1, this is position 2, and the third position is 3. So, therefore, here these fibers mostly on the top layer of the cylinder, they come and hit the Doffer surface, the end gets buckled and the fiber as a whole get transferred to the Doffer, and these fibers therefore will emerge as leading hook fiber. So, this is A 3 B 3, and the same way the fiber will move out and we call them leading hook fibers. So, these are the two mechanisms of the formation of leading hook, and we have already discussed the formation of trailing hooks, but there are so many different configuration of fibers. So, if we look at the characteristics of a Kahr's fiber, then we can write the fibers take a variety of innumerable shapes. Shapes are so many that actually is difficult sometimes to categorize them into only 5 categories. There could be many more categories, but broadly people have tried to classify them into 5 categories. Most of the fibers are not straight and neither parallel to each other nor to the axis of the fiber. Another point is fibers are entangled with each other, and a Kahr's fiber therefore is springy in nature. So, if you take a Kahr's fiber, either cotton Kahr's fiber or polyester Kahr's fiber, and if you pull it little bit, you will find it acts like a spring. The reason behind the spring is that the fibers are entangled with each other, they are bent and they are crimped and they are meshing each other, and hence the nature of the Kahr's fiber is very, very springy in nature. Now, we will be interested to know how can we measure the degree of disorder of fibers in a fiber. So, that if I change certain percent parameters and see there are some types of hooks are more in number than the other type, or overall parallelization or orientation of the fibers, whether they are different or not, we need a measurement technique by which we will be able to tell whether a change in process parameter or fiber parameter or machine parameter has made any difference on the degree of disorder of fibers within this fiber or not. the direct technique based on actually looking at the configuration of the fiber is very time consuming and very laborious. Therefore, we have to find out a simple way to measure the degree of disorder in fibers in a sliver. This is the technique which has been shown by some people. So, we try to understand this technique first. Let us take a sliver, consider a section whose length is less than the fiber length. So, this is the sliver. Let us take this section whose length is less than the fiber length. Now, let the fiber be straightened out by repeated combing and sorted out according to length. From this zone, let us say we take out this zone as if, and then we see the fibers within this zone are having different configurations. Let us comb out these portions of the fibers, and after combing, now let us arrange the fibers in order of decreasing length as shown in this diagram. Now, within this, any fiber whose length is greater than the section length, like this is the section length from here to there, which is equal to this section length. Any fiber greater than this must have been either bent, that means these fibers, they are either bent in the form of a hook within this section, or they are maybe twisted, or they must be lying in inclined fashion within this, and therefore, when you comb them out, they get straightened out and their length exceeds the length of the section. So, this part of the fiber indicates in a way the number of fibers which are in a bent shape or a hooked shape within the section that we have considered. So, we can get some indications regarding the extent of departure from orientations from the number of those fibers which extended beyond the section length. So, if we get more number of fibers in this category which are greater than the section length, we can say more and more fibers were not oriented along the axis of the sliver. So, number of these fibers, or one can also find out the weight of these fibers, can give us some idea about the degree of disorder of fibers in the sliver. From here, a technique was developed by a person called Nestle, which is a very simple technique, very easy to operate also. So, in this technique, what is there? There is a base plate here which is B, and on the base plate there are 3 plates P, Q1 and Q2, and the base plate and the plates P, Q1, Q2, they can be screwed together by these fly nuts. So, these are fly nuts. So, there are holes here which passes through this plate and goes further down the base plate. So, if I using the fly nut, we can remove these plates or we can tighten the plate against the base plate. The width of the plate P is around 1 inch. The width of the plate Q is around half an inch. So, what we do? We first remove the plates, top plates, and place a sliver. Once the sliver is put there, we may put 2 slivers or 3 slivers side by side. If we feel that one sliver is too thin, we can have 2 slivers or 3 slivers and place them side by side. while placing them we have to make sure that which side is the leading side of the sliver and which side is the trailing side of the sliver. That means, if whether this is the direction of delivery from the machine, then we must mark this side, so that it indicates that this is the direction in which the slivers were delivered. Now, what we do? We remove one of these plates. Let us say we remove plate Q2, but before removing we will cut this sliver along the edge of the plate Q2. After cutting, we remove this part of the sliver from here, and then we remove the plate Q2. And let us say after removal of the plate, we will see something like this in front of the clamp P. So, you see the fibers here, this is the cutting edge of, and there are fibers projecting out from the clamp. Many of those fibers are not straight and they are having different configurations. Now, we will use a comb and we will start combing this part repeatedly. While combing, we have to be little careful, so that in the sense that the fibers should not break. So, we comb them gently and repeatedly. After some time, what we find that most of the fibers will be straightened out like this, and the fibers which are within this zone from here to there, but they are not held by the clamp, they all will be removed, and this is the part shown as C here, that is combed out portion, fibers which are loose in this zone. And these are the portions fibers which are extending beyond the cutting line. Now, what we do? We put this plate Q2 back again and cut these portions, the portion which is extending beyond the plate Q2. So, if we cut this along this line, this is the portion, we call it E. So, E is indicating, let us say, the weight of fiber extended portion beyond the cutting line, and the part which is here is the weight of fibers in between cutting line and the plate. So, we see that the fiber which was here, now they have been classified into 3 groups: fiber C which are loose and combed out, fiber E which extended beyond the cutting edge, and fibers N which are in between the cutting edge and the clamp. These 3 quantities gives us some idea about the degree of disorder of fibers in a sliver. The indices which have been proposed are 2. One is combing ratio, which is C by E plus N, and the other one is orientation index 1 minus E by N into 100. These 2 indices gives us an idea about the degree of disorder of fibers in a sliver and also the level of their orientations. There are many more indices proposed by many people, but we are not taking them or we are not discussing them right now. Let us concentrate on these 2 indices. The question that comes to our mind is, what should be the length of the section S? What is S? S is this length. As I was told earlier, that length of that plate Q is typically half an inch. So, that length which is half an inch is basically S. Now, why S should be half an inch? This question will come to our mind. So, try to understand this now. Both the quantity E and C depends upon S. generally E is few milligrams, and therefore, it becomes difficult to measure E accurately when S is too small. So, if we try to put a value as too small, then the quantity E will be so less that there will be a lot of measurement error. To avoid that, we have chosen a length half an inch. The smaller value of S, the greater is the probability that a bent or hooked fiber will be cut, forming two parallel fibers, resulting in decreasing the significance of the measurement. So, this is the problem, and therefore, we want to make sure that S must be more than half an inch. At the same time, it should not be so much that it exceeds the fiber length. So, usually we keep the value of S close to half an inch for cotton. Some values of fiber disorder and orientation, like say in this case we see here what is the influence of section width or section length S. As the section width increased from half an inch to 5/8 of an inch to 6/8 of an inch, we see the combing ratio keeps increasing, orientation also keeps on increasing. So, this is how the two indices changes with increase in section width. Typically, the values which are chosen for section width is generally half an inch. Now, the comparison between these two indices, combing ratio and orientation index. Let us say consider a sample in which 80% of fibers are parallel and extend across the section, whereas rest 20% are perpendicular to it. Let us say there is a sliver in which 80% fibers are parallel to each other, and these fibers are extending across the section, and only 20% fibers are perpendicular to it. So, shear and orientation index will be in this case 0.25 shear, orientation index will be 100 since E will be almost 0. So, orientation index indicates complete parallelism even though 20% fibers are completely out of line. So, orientation index may not be able to make a proper judgment in a hypothetical situation like this. That is one of the difficulty with the orientation index. Though this is an extreme case, the same difficulty will be met in varying degrees with orientation index. If there is an appreciable proportion of crisscross fibers in the sample. So, that is the difficulty that we face with orientation index, and therefore, other indices have been proposed by others, but they are beyond the scope of this course. Combing ratio should not be much greater than 1 except when the fibers are very short. If shear goes beyond 1.5, orientation index should be regarded as having dubious significance. This is also we have to keep it in mind. Now, let us see the way the shear and orientation index values changes from card sliver to the roving stage as the sliver is drawn. At the card sliver stage, the combing ratio is 1.55, and as we stretch the sliver, go through the process of drawing and go up to roving, what we find here that the ratio goes down and down. So, you will learn later on that drawing is a process through which we reduce the number of hooks, and at the same time we improve the orientation of fibers, and therefore, we expect combing ratio to go down, which is reflected in this data. And also we can see that the orientation index also gradually is improving, that basically gives an indication that fibers are becoming more and more oriented towards the axis of the sliver or roving, whatever the product is. Now, come to the next important part of the discussion, that is NEPs. Discussion on carding machine is not complete without discussion on NEPs. So, NEPs are tiny entangled mass of fibers. They spoil the appearance of the yarn and the fabrics. The lesser they are, the better in a yarn, and therefore, we are very much concerned about NEPs. And carding is a process by which NEPs can be removed. We can eliminate many NEPs. At the same time, we must know that carding can also generate NEPs. So, carding is a machine which can generate NEPs, which can remove NEPs or eliminate NEPs. So, if there is a generation and there is a removal, then one may ask the question whether we should, whether there is a benefit in the carding process as far as NEPs are concerned. The benefit is there because the removal of NEPs are more in number than the creation of NEPs by the same machine. If the process is maintained perfectly, if the machine parameters are chosen properly, and if we maintain the machine correctly, then you will always find a reduction in NEPs in the cut sliver in comparison to what was fed to the machines. But if the machine is not maintained properly, the machine, the process is not set properly, then we may find tremendous increase in NEPs also. So, we have to keep in mind both the facts. Let us see how the machines generate NEPs. NEP formation is because of buckling of fibers during processing and sudden release of stored elastic energy, a result of stretching during carding action. Okay. It has been shown that the frequency of NEP formation is related to Euler's parameters, where n is proportional to f L squared divided by E into I, where n is the number of NEPs, F is the stress on fiber, E is the elastic modulus of the fiber, and I is the fiber cross sectional moment of inertia, L is the fiber length. What is I? Considering a fiber to be cylinder, I can be written as phi d square by 64, where d is the fiber diameter. In case of cotton, if the micrometer value is mu, we can write mu L equal to weight of fibers. We can relate it to the volume and density of the fibers by these equations, and from here we can find out the value of d square. So, putting the value of d in 2, we get I to be like this, and when I put I in equation 1, we get n in terms of fiber parameters, that is n is proportional to F stress level on fiber, L fiber length, gamma which is density of fiber, E as stated elastic modulus, and mu is the micronaut value of cotton in the case of cotton. So, what we see here that the number of NEPs that gets formed is a function of stress level and it increases with length of the fibers. So, we have to be very careful for a given fiber, what is the length of it and what is the level of stress that is acting on the fibers during processing of the fibers on the machine. Factors which affect net formations, fiber factors are fineness of the fiber, the maturity value in the case of cotton, the length parameter of the fiber, what is the length. In the case of cotton, another parameters which come is impurities in cotton. The other thing is the magnitude of tensile stress development on the fiber can also affect net formation, especially in the carding zone. So, any process parameter that increases carding force is likely to enhance generation of naps. So, we can try to analyze the various factors which can affect carding force. With the fibers, if we see, maturity plays a very important role and fineness also plays a very important role. The fibers as finer or the fibers immature in the case of cotton, then they can easily form naps, because the bending rigidity is also very low, they can easily get bent and take the configuration of the naps easily, and therefore, fineness and maturity both comes into picture. Length also basically facilitates the buckling or bending of the fibers within the carding zone, and hence length also becomes very important. And the other thing in the case of cotton is impurities in cotton. See, many of these impurities also gets counted as naps by the instrument. The other thing which could be problematic is that the impurities are there in the cotton. The impurities sometimes they get lost between the wire points of cylinder, and therefore, the cylinder loses its opening capability, and hence the fibers which are coming from the lacquer inside, they are not getting separated or opened out properly by the teeth of the cylinder, because impurities have completely filled up maybe the spaces between the wire points, and therefore, all those wire points will lose their opening capability. The fibers will be there on the tip of the surface of the teeth, and they are not getting penetrated by the teeth properly, and hence there will be difficulty in separation. So, therefore, these parameters of the fibers are very important from the point of view of nap formations. The other thing is the stress level. So, this stress level during carding, especially the level of stress which acts on the fibers between flat and cylinder is very important. So, there what matters is the space between flat and cylinder. If the fibers are long, there will be lot of force development on them, because there will be lot of entanglement between the fibers, a lot of friction between the fibers and the wire points of the cylinder and flat, and hence carding force will rise with the length of fibers. Similarly, if the space is too narrow between cylinder and flat, then also the carding force will increase, and if we increase the cylinder speed, also this carding force will increase. So, all these parameters, cylinder speed, the setting between cylinder and flat, the length of fibers are important from the point of view of carding force also. So, we have to ensure that the carding force do not go too high. In that case also some naps may be formed. Why these naps are forming? Because of the carding force. The fibers get stretched by the force, and when these fibers are released suddenly, then the internal stress which is there in the fiber, that stress will cause the fibers to buckle due to sudden release of the energy which is within the fiber, since they are all stretched. And therefore, when they try to buckle because of sudden release of the energy, they themselves will get bent, and also they may bring some other fibers which are close to it and put them together and create a knot like fibers which we call naps. So, the more the force is created, the more will be the internal stress on the fibers, and more will be the energy within the fibers, and hence possibilities of buckling when the due to sudden release of the force will be tremendous. So, this is what is therefore important. The next point we go to the some nap data in the case of cotton. What we see here, for different size of the naps, we can see the nap value in case of bale, card feed and card sliver, and we see here that from bale to card there is increase in card feed, there is increase in nap, from card feed point to card sliver point there is a decrease in nap. Therefore, ideally naps will be removed by the carding machines, and the removal efficiency can go to the extent of 74% in the case of fibrous naps, and for seed coat naps it can go to the extent of 60%. Reduction in average size of the naps could be 13.5% for fibrous naps and 21% for seed coat naps. So, typically this is what generally is observed when the machine is properly maintained, that the from bale to card sliver, if we see, there is always a reduction in naps. Average size of naps at different stages of processing, like in the bale it is average nap size is 746 micrometer, card feed 724, card sliver 626. So, there is a reduction finally at the card sliver stage. Same will be with the numbers 206, 369 and 97. Size of seed coat naps also, if you see, there is a reduction here. Number of naps per gram seed coat naps, also there is reductions. That means, from these data we can conclude that the carding machine, if it is properly maintained, process is properly chosen, we will find a reduction in nap size with respect to the bale, we will find a reduction in number of naps with respect to bale. So, the machine can reduce the number of naps, though there is some possibility of nap generation by the machine as well. This diagram gives us an idea about the nap reduction as a function of size of the naps. Now, if we look at this data, then we will see that very small size naps, if we classify the data in two groups in terms of size of the naps, and we say that this side there is an increase in naps, whereas on the lower side, this side the values are decreasing. As the size of the naps are increasing, there is a decrease in size from with respect to feed. So, what we feed to the machine and what we see in the card sliver, there is a reduction, and this ratio of reduction is shown here by this particular plot. it basically means from here that bigger size naps are reduced to very large extent, but there is increase in small size naps. And why there is increase in small size naps? The possibilities are two. One is it is difficult for the machine to remove the small size naps which are 200 micron, 300 micron or 400 micron in size. The other thing could be that big size naps are broken into pieces and part of those big naps become small size naps now. So, their numbers though reduces, but small size naps increase in number because these bigger ones get splitted into smaller ones now, and hence we may find a net increase in the number of small size naps. So, that is the reason why we find increase in naps in this region, whereas we find a decrease in naps in this region. With that, we close today's discussion, and thanks.